I hope it's okay. So recap from the last time. So we start talking about Chern-Simons theory, and we consider on three-dimensional manifold, and we consider the three-dimensional manifold with boundary, which is two-dimensional manifold, and on the Chern-Simons theory on the three manifold with boundary, at the boundary, however, was the Miller-Witten model, where GE is a map from the manifold to the gauge group G. Okay. And then it said, and then so in the homework you guys showed that the K has to be integer in order for the partition function to be well defined. And you guys submitted had a homework this today, hopefully. If you want to hand in, you should hand in to Ye. If you're handing, submit online, it's okay. And so you guys show K has the integer, for the partition function to be well defined. And in particular, so the Chern-Simons theory is the topological quantum field theory, which is independent of the metric G, metric of the three manifold. And then, so the typical feature of topological quantum field theory is that the partition function is the element, the vector, one vector at the vector space, finite dimensional vector space at the boundary. And in particular, so if you have a four-puncture sphere at the boundary, give a space S2 with the four-puncture dimension has to be two dimension. So this comes from single box, and in the middle you have a fusion role. So in the quantum mechanics you have a spin-1/2 space system, spin-1/2 system. You have a three-dimensional. So this T times 2 is equal to 3 decomposed 3 times 1. So one is the in the single box times single box representation of the SU2 is horizontal double box times vertical double box, and then so you just 3 corresponds to plus plus, plus minus, minus plus, and the minus minus. So that's what you learn. So these are the basis of three-dimensional representation. And in one dimension, you have a basis plus minus, minus, minus plus. Okay? So this is one-dimensional space. So that's what you learn in quantum mechanics. So if you take the tensor product of the spin-1/2 system, you have either horizontal double box or vertical double box. Okay? Vertical double box. So that's another way to say the representation. Spin-1/2 representation times spin-1/2 representation is indeed spin-1 representation plus spin-0 representation. So that's another way to say to quantum mechanics. So you have a two choice in the middle in the channel. Therefore, the dimension has to be 2. So you have two choices. So you have a. So therefore, if you have a Chern-Simons theory on a following space, the four-puncture sphere. So one is the Wilson loop is positive crossing, and at the boundary you have a four-puncture, and also you have another. So you just have just no crossing, and then you have under crossing. So under crossing, and then so you have 3 states in Chern-Simons theory, but at the boundary you have a 2 dimension. So therefore, so if you have 3 states, they have to be linearly dependent. So it's a vector space. So it's they have to be linearly dependent, and then one has to show the quotient alpha beta gamma. And to show the alpha beta gamma, so you have to use the braiding operation So if you do the braiding, so if you just braiding, you just rotate the two ends. So if you swap these ends like this way, so if you have a two crossing and rotate the upper two, then you get the. If you just crossing like this way, okay, crossing like this way, you bring this state. That's called braiding operation. Braiding. So this state, so let's go L plus, L minus, L0 and L minus. Okay. Then, so you have a braiding acts on L plus, you should get the L naught. Okay. So you just undo the crossing. And furthermore, if you do the one more braiding, you get the undercrossing. Okay. So therefore, B squared L naught, L plus is B L naught, which is L minus. Okay. And B, this braiding is indeed just the matrix that acts on this two-dimensional space. It's a Hilbert space. Okay. It's a 2x2 matrix. It's if you have a 2x2 matrix, so this is the braiding matrix. 2x2 matrix. Okay. And the 2x2 matrix is just a usual matrix calculation. They obey the following relation. Trace B and B plus determinant B is equal to Z. It's just the ordinary, if you just start with B, A, B, C, D, and just plug it into here, this satisfies. This is, of course, identity matrix, 2x2 identity matrix assumed. So now, so we just act this matrix on the L naught, L plus. Then what you get is clearly L minus, minus trace B, L naught, and then plus determinant of B and L plus is equal to 0. Okay? That's what you get. So as you can see, so I already explained it. B acts on L plus, you get the L naught. So you just put everything L plus, and L plus, and you get this relation. Okay? And this already look like a scaling relation. I draw last time. And then, so what you need to determine is B, this B. So this B is 2x2 matrix, and which is diagonalizable, and then you have to, so this one I just borrowed from the representation theory, and the Q is, again, exponential. The last time I explained 2 pi I divided by K plus 2. So now we assume that G, group G is equal to SU2. Okay. SU2. And it's 2x2 matrix, and which can be diagonalizable along these bases. And so here you have to use some sophisticated technique for use the representation theory, which I'm going to omit. Then, so if you just plug into here, what you get is L minus Q plus, Q minus Q to the cube. So that's trace, right? Trace. And L plus, L naught. And plus, you just take the determinant, you have a Q to the fourth. L plus is equal to 0. Okay? So then, from here, after some simple manipulation, you get the Q square, L plus minus Q minus 2, L minus, and then is equal to Q minus Q inverse, L naught. Okay. So this is exactly what I have written last time in the end of lecture. So this is the really scaling relation of Jones polynomial. Okay. So this is exactly what I have written last time for Jones polynomial. From which I have calculated Jones polynomial of the, so this S3. So S3, we have a knot. So that's called trefoil. And the question is how you compute Wilson's loop expectation value along this trefoil K in transamination. Even though this is the infinite dimensional integral, so this is again the class integral dA e to the I transaminant Wilson loop. Okay, so this is the infinite dimensional integral, but if you use the property of topological quantum transaminant theory, where the Hilbert space at the boundary is finite dimensional, even though it's infinite dimensional, one can evaluate the Wilson loop expectation value exactly. So this is how you obtain the scaling generation by using the property of TPFT. So as I mentioned, so this is the work by Witten in 88, by which this is one of the reasons why he got his medal. And this scaling generation is obtained by 1984 by Vaughan Jones. He passed away unfortunately like a spread 1 or 2 years ago. He's an Australian mathematician, and he introduced this scaling generation in 1984, which gives the invariance or not, and we then interpret this Jones polynomial in 1988 by transaminants. So this is a very typical instance of topological quantum field theory. So that here we particularly use this phenomenon. So even though it's the infinite dimensional integral, if you use the relation of path integral is inside the vector, define the vector inside a finite dimensional vector space, then one can evaluate the partition function exactly. So this is a typical feature of the topological quantum field theory. And then, so this is written both 88, and then again, one of the great mathematicians formulate topological quantum field theory axiom. So here, TPFT axiom by Atiyah. The same year. Actually, Atiyah asked Witten to interpret Jones polynomial in terms of in physics. That's the Atiyah. As far as I know, Atiyah visited Institute for Advanced Study at Princeton around the 87, 88 several times, and then he gave the problem to Witten, and Witten solved it. The so-called famous restaurant in the Swansea in the UK, that he met the Ziegel and then also Atiyah at the famous Annie's restaurant to solve this Atiyah's. He solved the Atiyah's homework, and they met in Annie's restaurant called Annie's, and he just reported that Atiyah and Ziegel. But unfortunately, this restaurant is already bankrupt, and then they disappeared. That's what I heard from Hitchin. Anyway, so Atiyah gave a TPFT axiom. So this is typical feature of TPFT axiom. So you just consider the TPFT on D plus one-dimensional manifold M. then, so you just associate with boundary. Well, boundary manifold with sigma is of course a d-dimensional manifold. And then you just associate the partition function. So y, is the partition function of TQFT is defined Hilbert space of sigma at the boundary sigma, where this sigma is finite dimensional vector space. So vector space, and if it's satisfied, so this is actually sometimes called TQFT function, but in physics language you can identify this is the partition function of this m-dimensional, so d plus 1 dimensional manifold. And it satisfies the following property. Okay, so if you have, so what I have the picture in mind is the same thing. So you have the d-dimensional manifold M, you have a boundary sigma, associated boundary sigma, and then if you have, if you write the minus sigma as the minus sigma for orientation flip, reverse. Then, so here is space associated the orientation flip sigma is a dual vector space of sigma itself. Okay, it's a dual vector space. You have a vector, you have a dual vector space. So in particular, so if you have it, so and also for disjoint union, you have tensor product. As a vector space. Okay. So in particular, if you have a cobordism, you have a two manifold, sigma 1, and another manifold, sigma 2. That's okay. And there is a manifold in between. That's called cobordism. If you consider such a situation, then TQFT function or partition function M is inside the sigma 1 times sigma 2. In particular, so here, if you consider the orientation coming from the d plus 1 dimensional manifold, one orientation has to be, so this orientation has to be reversed from here. Okay? So that's easy to see, right? So when you have the boundary, okay, so that comes from the orientation coming from the come from M3, M, and then once you just hit in the one boundary, you have the normal vector is this direction, so it's inside M. On the other hand, if you go to the top boundary, you have the normal direction is the outside of the manifold M. Okay, that will give you the orientation reversal to one end to the other. Okay? So therefore, you have to associate minus. Minus sigma 1. So this is indeed the dual to the dual vector space sigma 1 cross H sigma 2. Okay. So that's coming from the first property. Okay. First property. And then, so what's this object? So it's a vector inside of this tensor product. So vector from dual vector space to another space, vector space is indeed the map from sigma 1 cross H sigma 2. So that's a linear map. So it's a vector space. So dual is natural pairing with original vector space, give you another vector, okay, in the D. So this one can be contracted with this vector, and the tensor product will give you the element in there, in the other. So therefore, so as you can easily see from this picture, so this, if you have a cobordism, you have a vector space H. Let's use some color chalk. So H sigma 1 to H sigma 2. So that's a linear map. So given a manifold with the two boundaries, the TQFT, topological quantum field, will give you a linear map from one end to the other end, as a heuristic. Okay, and then so what if you have a two copy of cobordism? Two copy of cobordism. So you have a two copy of cobordism. So what M1 and sigma 1 to sigma 2, and then maybe minus, and another copy. So you have a two copy. This is minus sigma 2, and you have another copy of another D plus one dimensional manifold, which has some other topology sigma 3. And of course, you can glue them together. So you have the d-dimensional sigma 2 and the opposite orientation. Okay, you can glue them together. Okay, by an identity map. And what you get is of course some composition. So this is M1 composed with sigma 2 glued with M2. Okay. M1 and M2 are glued along sigma 2 by identity. Okay. And you have another D plus one dimensional manifold where the boundary is minus sigma 1 and sigma 3. So we now know, so this manifold will give a map from H sigma 1 Hilbert space to the other Hilbert space. And this manifold will give you the the linear map from one Hilbert space to other Hilbert space. Okay, what does this guy do? So the sum map Z, we call it ZM1, and we call it ZM2. And I should write down here is ZM1. This is a linear map manifold. So what this manifold would do? So if you have glued them together. Good. So this manifold will do the composition of these two linear maps. H sigma 2, and then you have the composition M1, and then Z M2. Therefore, what you get is Z M1 glued along sigma 2 with M2 is indeed the composition of the linear map. So it's just metric multiplication. So it's a map from finite dimensional vector space, Hilbert space to finite dimensional vector space. So this can be understood as a matrix element. So some matrix element. So therefore, if you have a gluing of two manifold, you have a matrix multiplication. Okay. And in particular, if you have some cross manifold, if you have cross manifold and maybe you can cut in the middle. Okay. But here you have an empty space to empty space. So, okay. So empty space to sigma to empty space. Okay. So for empty space, we associate Hilbert space as a number. Okay. Hilbert space of empty space is some number. Okay. So therefore, so this number to Hilbert space, so if you have cross manifold, so if you have a cross manifold M3, so sorry, M with the boundary is just empty. Okay? So it's a cross manifold. If it is closed, it's called cross manifold. Then it's just partition function is a linear map from C to C. Okay? At the end of the day, so empty to empty. Okay? So therefore, it just gives you the number. Just number. The map from C to C. So it's just a multiplication by number. So it's the for cross manifold you have a C. And then you have just a how to say manifold sigma times segment. You have a sigma times just the same copy. If you have just a segment, it's just a 0, 1 segment. It's just direct product of the sigma. Then, as you can easily imagine, so you have a Hilbert space to Hilbert space sigma. So it's just identity. So this is identity. You just associate identity matrix. So therefore, if you have the partition function of sigma cross I, segment, the direct product, so this is just an identity matrix on the Hilbert space of associated sigma. So this is the TQFT axiom. So this is composition. So the composition is 3, and 4 is you just associate empty manifold to the number. And you have the, this is the inside territory of 4. And number 5 is just if you have a direct product with segment, you have identity matrix. So, and in particular, so if you have the S1, sigma cross S1, so this is cross manifold, there is no boundary. So you have to identify left one to the right one. Just by gluing. So if you identify left manifold and right manifold by identity, you have sigma cross S1. Okay? So it's a cross manifold. Okay? It's cross manifold. Okay? And then, since if it is a cross manifold, the TQFT functor or partition function has to be number. Has to be some number. And how do you compute this number? Good. Since this is the identity map, if you have a just direct product, you have identity map, and you just identify left component and right component by gluing. Okay? So therefore, you have to identify left Hilbert space and right Hilbert space by identity map, which is just a trace. Trace of Hilbert space of sigma times identity. And what's this object? So identity means identity in the here. So it's a matrix 1, 1, 1, dot, 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 1, and this matrix is the size is dimension of vector space. Okay. Therefore, if you take trace, what you get is dimension of Hilbert spaces. So that's the consequence of the TQFT axiom. And the Chern-Simon theory all follow this axiom indeed. By using this axiom, one can compute the many quantity. As I mentioned, with some loop exponential value, and then growing, and so if you have some knot and take trivial neighborhood, okay. So this knot is S1 embedding inside S3, okay, S3, and if you consider the thickened trivial neighborhood, you get rid of it. So you just get rid of some thickened trivial neighborhood around the knot. And the boundary, so the boundary is, of course, you just thickened the S1, so the circle. Boundary is, of course, torus. Okay? The boundary is torus. And you can group, you just bring another solid torus and then group them back by some non-trivial map from torus to torus. So as I mentioned, and also I'm going to explain, so there's a SL2Z action, as I mentioned, so SL2Z action on the torus, right? T2, as a different. So you can just peel this solid torus into here, okay, to get some non-trivial manifold M3, to get the non-trivial manifold M3. And then by using this TQFT axiom, one can compute partition function in principle for arbitrary three manifold. That's the power of this TQFT axiom. So this is the 1988. Right after the Witten work, Atiyah just gives the mathematical framework for topological quantum field. Okay, so this is the part I missed last time. So any questions so far? Okay, is it okay? Okay, so then I will move on to some a bit more sophisticated subject, so-called modular space. Okay, I think before then, you guys are interested in what's the content of final exam, I would imagine. Shall we talk about before moving to the next topic, shall we talk about a bit of final exam? Okay, let's talk about it a little bit. So it's the same time next week. And as I mentioned, so the problem itself is very simple. So just decide without looking at any reference. So is it I don't know. Let's go. I don't know the terminology. It's a B-shu. Is it correct? Or B-juan? B-juan. Okay. I think like this way, right? Correct. B-juan. At the same time, and then the problem itself is very simple. So I already created. So the one is anyway. So you cannot bring anything. So you have to solve by yourself. But all the definitions and the necessary tools and the formula are given. And so one section is about the manifold, about concerning manifold, and another second section is the vector field, and then differential form. So another is the homology group. So another section is the Riemannian geometry. Anyway, so the problem itself is simple. So you just quickly review my lecture note. So that all of these sections, so that you can be prepared. But don't worry. I mean, you guys did the really difficult homework every week, which I'm pretty impressed. Actually, yeah, I have to say that the student this year is better than the on average. This is the third time to teach this course for me, and this is the first time. The previous 2 times this course is only 2 credits, so I just need to teach only less than 2 hours. This time, so I have to teach 3 hours, less than 3 hours. But anyway, you understand, right? 3 classes. Equals 3 节. So this time, so it becomes actually I asked the department to increase the hour. This is the first time to teach 3 节 course for this class. So it contains more content. But students this year did pretty good job than the last 2 years. So I'm pretty impressed. So yeah, so and you guys have done lots of difficult homework, so don't worry so much. And also, yeah, don't worry so much. Every week you guys spend a sleepless night to solve the homework. So don't worry so much. So the problem are way easier than homework. So that's why I just decided to use the teaching. So that's the plan of the final lectures and the final exam. Yeah. Oh, and then so as I mentioned in the WeChat, so the lecture notes are updated and I posted in the e-learning. So from now I'm going to talk about the modular space, but that part is added into the lecture notes. So you can take a look at the e-learning for lecture notes. But yeah, so and I will send the solutions to this week's homework by the end of it, maybe tomorrow. So, but if you haven't submitted yet, so you should submit as soon as possible, so that you can get the tool. Okay, so that's the announcement about the final lecture. Okay. Any question about the final exam? Anyway, so yeah, you can just briefly review my lecture notes around this section, and stay relaxed. I mean, it doesn't, and it's just an exam. Okay. Any question about the final exam? Okay, so let's talk about modular space. So we already saw lots of example of modular spaces. People just keep asking what is a modular space and what is a modular space. The modular space has a very important role in even physics, so-called modular space of vacuum. So we will talk about the so-called modular space. The notion actually dates back to the Riemann in 1954. 1957. So no, 18, sorry. 1857, the Riemann, where he defined the so nowadays called Riemann surface is two-dimensional surface. He defined as a complex manifold. And then he just considered the space of the shape, indeed, of this two-dimensional surface. And he already noticed, so that he called a moduli. So the space of this Riemann surface, I'm going to make it a bit more rigorous in this lecture. So he defined the so-called, introduced the notion of moduli. But to mathematically formulate and also to treat it as a geometric object, it takes a lot of effort as the brilliant mathematician. And then it takes century indeed. 1960s, there's one genius called Mumford. Defined the so-called nowadays called modular space of Riemann surface in algebraic geometry. And also 1970s, another genius, both of his medalists, System, treat this modular space of Riemann surface as using hyperbolic geometry. So it took century to formulate Riemann's idea. So it's Riemann is a very, very influential figure. His idea is almost always correct, but to formulate mathematical rigorous way, it takes a century. It took century for even mathematician to formulate. And this modular space of Riemann surface will be it becomes very important even in physics, especially string theory. So now there's a Witt and Kontsevich. Nowadays called Kontsevich theory. It's related to so-called two-dimensional quantum gravity. And both of you similarist. Okay, so if you understand the modular space of Riemann surface, you will get the field level. So this is the around the 90, and which is related to two-dimensional quantum gravity. And this appears if you take my string theory course tomorrow and so on, or take a look at the video. I already introduced the notion of the modular space of Riemann surface. But anyway, so this modular space is introduced by Riemann. So this is a historical background. But we already saw the modular space of Flock connection. So the last lecture, I introduced so-called modular space of Flock connection. So modular space of Flock connection of the manifold M of gauge group G is indeed the morphism of pi 1 M to the G divided by G. So it's the space of linear map homomorphism for fundamental group of M to gauge group G, and you take quotient by adjoint action. In particular, we just saw modular Flock connection of torus of SU2 gauge group. This is indeed S1 cross S1 mod Z2. That's what we already saw. And then, so we just see this is indeed give you pillowcase. So if you consider family of Flock connection, and then so the modular space of Flock connection parameterize the Flock connection over the torus, and then so what you have is the identification of T2 mod Z2 by just identify this red strip and this without color strip And then at the end of the day, so you get the pillowcase. Where there's 4 singular point up here, okay, that will give you the corner of pillowcase. Okay, that's what we already seen. So therefore, if you parameterize flat connection, that's called modular space or flat connection. Somehow, this parameterized space itself has some kind of topology. Even though there is a 4 singular point. And this 4 singular point is, at these 4 singular point, something special occurs. Indeed, you have, so this torus has a fundamental group is, as you already know, so you have A cycle, and B cycle, the B cycle, and then A cycle and B cycle are map. So A cycle and B cycle, the generator of this fundamental group, and G is SU2. So their map indeed at these 4 singular points is plus minus identity map inside SU2. Okay. So this is really the invariant under Z2. So Z2 is swap eigenvalue, right? As you know already. So this Z2, once you swap eigenvalue, it stays as it is. Okay? So therefore, it's a Z2 invariant point. Okay? So that's the what happens in singular point. So this is one notion of the modular space, but it still looks like ambiguous. So let's do a very simple exercise. So the modular space, is actually, you just consider some space of some object. In this example, space of the A is a flat connection, and you just take equivalence class. In this example, equivalent class is adjoint action of G. Okay? A is the flat connection, which is the map from fundamental group to G, and then the equivalence class is adjoint action. And furthermore, you can consider lots of examples. For instance, the simplest example. So let's consider a toy example. So you just consider space of some object, whatever it is, and impose the equivalent relation and classify. The modular space classifies some object up to equivalence relation. So that's a philosophy. So that parameterizes some object. So for instance, if you consider A as the space of linear space or vector space, okay, and the equivalence relation is the old linear map, isomorphism. So namely, so you have vector space B, you have a GL, action of GLB. So it's in this invertible matrix, essentially. You just want to classify them. Okay. Then A mod is what? All the vector space up to linear isomorphism. Huh? Then what this modular space is? Good. So this is just a classified dimension. So B is everything up to linear isomorphism, everything R to the N. Okay? up to linear isomorphism is just R to the n. Any vector space is isomorphic to R to some power. Okay? Therefore, the choice is only here, the n, the dimension of the vector space. Therefore, this is indeed a natural number. Okay? Natural number. So modular space or vector space, all the vector space, you just consider all vector spaces. After linear isomorphism, it's just classified by dimension. It's very simple. So therefore, dimension is just natural number. So that's the modular space. Another example. So cross-oriented two-dimensional surface as A. All the cross-oriented whatever it is, this kind of stuff. And the equivalence relation is the diffeomorphism or homeomorphism. Which is the one-to-one differential, continuous map, okay? Continuous map. So then, so how do you classify a cross-oriented surface up to the homeomorphism? So this is classified, everything you classify genus. Okay? So everything, all the Riemann surface, even though torus like this one is a bit different, look like different from identifier like this one, right? This look like, if you embed torus into the R3, this has a curvature. Okay? At each point you have you have a curvature. But this one is just flat. There's no curvature. But they are identified by homeomorphism. Okay? Okay? Homeomorphism. So it's an invertible map. So everything, anyway, so even like whatever, I don't like, it's it's too common. So as you know, so this coffee cup is also, it's too common to say, so I don't like this example. But this one is really the same as torus, but up to homeomorphism, okay? Homeomorphism, okay? But they look like different, but up to the homeomorphism, they're equivalent, okay? So that everything is classified genus. Okay? So therefore, genus is indeed a natural number. Boring example. Let's continue. Let's continue. Third example, A is the line in vector space, which means that the vector space V is spanned by the linearly independent of the basis. Line is just a okay, so line is just pick a vector V, and then line is just A times B, where A is inside R. Okay? So you just look at the space and just, oh, sorry, this is not true. A plus B, and B is R. So roughly speaking, you have the vector space you have origin, but whatever. So pick B. Line is like this way, okay? I mean, somewhere around the point B and the vector V. That's a line. So V is a pick a vector V, and you just take the translation by point B. Okay. And then equivalence creates a affine transformation. So this is rotation. Sometimes people go, in physics it's called Poincare transformation. Rotation plus translation. Okay. Rotation plus translation is called affine transformation. And then so all the line can be mapped to by affine transformation by just the x-axis. Okay? All the line can be bring it to here, this red line. Can you see that? So just bring point B to the origin by translation, and then rotate the line to the red line by rotation. Okay? So everything, all the line can be bring to this red line by affine transformation. Okay? So therefore, only you can have one line, and all the lines are equivalent. Okay? Therefore, A mod tilde is indeed a point in this example. Okay? So modulus is very simple. It's just point. Point stands for this red line. Okay? And this is a very boring example to warm up the exercise. Okay, now just let's gradually make the problem difficult, make the problem more difficult and more interesting. Okay, so let's consider A is all sphere. Let's consider n-dimensional sphere. Let's specify dimension sphere. And the equivalence class is isomorphism. Isomorphism. Okay, a sphere is n, and there's some standard metric G. This is standard metric from R. From n plus 1, you already did many exercises by using as n-dimensional sphere, and you just consider isometry. So let's consider the following. So the question is how you embed Okay, so I think I shouldn't use the standard actually. The only metric, okay, sphere and the metric from R n plus 1. Okay. And if you consider isometry, okay, isometry, you cannot distinguish with the sphere with different radius. So in other words, x1 square, let's call x0 plus x1 square dot xn square is equal to r square. So isometry is only of the sphere is what? Isometry sphere is what? Isometry group of sphere is what? Good. It's O n plus 1. Okay. So isometry is also only rotation, which is generated by rotation, okay? Which does not change radius, okay? So if you change the radius, these two spheres are distinguished, okay? Because we only impose isometry as an equivalence relation. So therefore, modular space of this element equivalence relation is indeed what? So its parameter is this radius r. Okay? So therefore, this is precisely speaking positive real number. So you cannot take 0. And at each point of the modular space, you have a, so this is schematic, you have a, at each point, you have some sphere with radius r. But if you move to here, you have a bigger sphere. Okay? Like this way. At each point of modular space, you have a sphere. And if you go to the, okay, sorry, I've been a bit schematic. So it becomes like this way. So this, the length is essentially, anyway, so I mean, I'm being schematic, just radius r at point r. Very simple so far. But this is the modular space in this case. You know what happened in 0? The boundary of modular space. So if you consider the modular space closure, this is actually origin. If you take closure of this modular space, it includes this 0 and get rid of all the modular space. What happened in this point 0? The sphere shrinks to the point. So no longer it's sphere, it's just point. Sphere degenerates to point. So at the boundary of modular space, always something special will occur. Okay? At the boundary of modular space, something special occurs right here. This is generic feature of modular space. Now what if you go to the infinity? So if you just consider you embed M inside R and infinity. Okay. If you embed R plus infinity, so infinity is just plus infinity, and take the closure, then in this case it's 0 and infinity. So we already know what's happening at the origin. That shrink to the 0. What happened in the infinity? What's going to happen for this sphere? Huh? Just speak up. Can you speak up? So sphere at the infinity becomes plane. So it really, the infinite dimensional radius of the sphere can be understood as a plane. Okay. So when you do the stereographic projection, So you just identify the point and so on, right? Okay, point and so on. So this plane can be understood the sphere with infinite dimensional radius. Okay. So at the, if you consider the infinity as a boundary, so again something special happened in the modular space. Let's consider another example. So we already see another example. So another example is A, these lines in Rn equivalence relation is translation. So the previous example, where was it? Oh yeah, number three. So we just considered lines in vector space V. Okay, well maybe I should call it vector space V. Okay. Which is usually as isomorphic to Rn by linear transformation. But the previous example, we add equivalence correlation as a rotation, but I get rid of this condition. So what's going to happen here? So what is the modular space? Huh? Sphere? Okay, so you can always bring the line by translation to the origin, okay? Okay? So the line in Rn inside R, okay? Even if you can rotate, okay? If you go back to here, if you do that 180 rotation, you come back to original one, okay? So therefore, SO, as I mentioned many times, is SO n minus 2 times. Okay, so I think I should use this one. So as a homogeneous space, ON. Sorry, I think I should call it. This is ON. ON plus 1. So if you consider, sorry, I think it should be ON and then ON minus 1, sorry. So ON acts as the isometry group, okay? As a rotational group on Rn. And then the subgroup that fixes this line is the one that is orthogonal to the rotation orthogonal to this line, okay? That rotates or is a subgroup. And also there's another subgroup that actually swap by 180 rotate 180. So this is Z2. Okay. So therefore, this modular space indeed Rpn minus 1. So projective space, now it's getting a bit more interesting. So projective space can be understood as a modular. We know this space, one can introduce so-called Riemannian metric. Also, this can be understood as simplex manifold, and so on. Oh, sorry, I don't know whether it can be understood as simplex manifold. But I know Cp n minus 1 is the simplex manifold. Okay, anyway. Anyway, so we already know that the RPN minus 1 has a lot of structure, and you can treat it as a manifold. Okay? We already know. So if you consider modular space of line up to translation, the modular space has some already structure. You can put some structure on to the modular space. You can treat it as a geometric object. So therefore, so RPN, so for instance RP2 is something like a and then you just identify this red one and then purple place. So you just identify. So you just identify northern sphere and southern hemisphere by Z2 action. So you have just northern hemisphere, but equator you have to identify red now this point is identified at this point. Okay. This point. So red circle and the purple circle you have to identify. Okay. At each point of the RPN, you have line. Okay. At each point, so like we saw here, at each point of modular space, you have a sphere. At each point of modular space, you have a line. Okay. So you can complexify. So complex line inside a complex vector field. Then it becomes C to the n. And then of course the modular space is indeed CPN minus 1. If you complexify. Okay. So then we already know this can be treated as a symplectic manifold. So it has a lot of structure. So let's generate a bit more. Bit more. Okay. Let's consider a bit more, generate a bit more. A is a line in vector space. In B, which is isomorphic to the n, equivalence nothing, nothing. We want to classify all lines inside the Rn. Okay. So let's consider the first of all the lines that pass through origin are parameterized by RPN minus 1. That's we already seen that. So then the lines that go through, so the line goes through the origin is already, we know, that is already anyway. We already know they are parameterized by RPN minus 1. Okay, so now the northern hemisphere and southern hemisphere are identified. But the line can be translated, okay, from origin. Okay? So therefore, so as I mentioned above, you need to specify a line, you need to specify B and then translation. Okay. So once you specify, so here, if you pick the point in the RPN minus 1, it's the same as the specifying B vector B. Okay, up to equivalence generation minus b. Okay, that gives you the same line. That gives you the same line that pass the origin. But one can translate. Okay, translation is just orthogonal to this. Can be parameterized the plane that is orthogonal to this plane. Oh my goodness! I think what my writing is horrible. I think let me write down. So the orthogonal to this line is indeed something like how to say. Okay. And then the plane look like. This. So the plane, this red plane, is indeed the orthogonal, perpendicular to this line. Okay, so that you can just translate along this red line. So you can just translate like this way. Anyway, freely, like this way. Anyway, I think we just write down like this way. Maybe I think that's more easier to see. So this translation will give you B over there. Okay. So therefore, this plane is orthogonal to this line, which is tangent this point. Okay. If you bring this plane to the point here, it becomes tangent. It becomes tangent vector at this point. Okay. And you specify the point in the tangent space, you have a one line. Okay? So therefore, modular space, even if you don't impose any relation, modular space of line, then you don't need to impose anything, is indeed tangent bundle of RP n-1. You understand? At each point, you have a tangent space. If you pick a point at the tangent space, you have a one line. Okay? Similarly, if you take some other point, you have another line that specifies vector b. Okay? And if you consider the tangent space on that tangent space on this point here, and the pick point here, then you have some other line, okay? That specifies vector b, okay? B over there. So therefore, more strictly speaking, I should write down b is this one. Oh, sorry. So okay. So therefore, a is real number, and then b is indeed vector. Sorry. I think I should write like this way. Sorry. Okay. Okay, so therefore, tangent bundle of RP n-1 can be also treated as the modular space of line. Okay? Therefore, the modular space itself has some topology, non-trivial thing. So what we have learned is somehow can be treated as some modular space. Okay, so I'll just give you one example and take a rest. Let's take a rest. So I shouldn't erase around here. So you can even consider more special thing. A is R-dimensional subspace in Rn, and the equivalence generation is the again maybe affine can be affine transformation, or maybe can be just translation. and or you can have nothing. Again, from here, you have a modular space is indeed a point. And this one is more interesting object. So you just consider some subspace R to the R subspace inside Rn. Okay? When small r is equal to 1, it becomes projective space. Okay? However, if R is not 1, so it becomes some cosine space, as I mentioned. It becomes n-dimensional divided by O n minus R. And you can easily imagine the construction over there. So this is, indeed, we know this is R P n minus 1. Okay? We can mimic this construction. N minus 1 and O1. And this is when R is equal to 1. Small r is equal to 1. Well, therefore, we can just mimic the construction. Okay? So the O n minus R is the rotation. So this is R dimensional subspace. Rotation orthogonal to this subspace R to the R. Rotation. On the other hand, the rotation of O of R is a rotation along this subspace. This will act on the rotation along this subspace. That doesn't change this subspace. So therefore, this subspace subgroup is stabilizer subgroup of this subspace R to R. And indeed, this cosine space has a name, which is called Grassmannian. Real Grassmannian. And then, so this is also very interesting. Space, but it's a bit difficult subject space, so that in my lecture I didn't treat, but in research often show up. And again, so from here, modular space. So this is modular space. And the modular space without anything is again tangent space of Grassmannian Rn. Okay, so let's take a rest and move on. 10 minutes break. And if you have a question, just let me know. Do you have a tissue? Okay. This is much better. Yes.
Well, we're doing calculations. This is a joint action G on A, and this is a moral pattern form. However, in the middle of the process, we will come across like only this show up, and I don't know if it's a legal expression. It belongs to the it belongs to the legal, and this is a legal algebra. Why can we directly?
You want to show that the F to this. You want to show
Yes, but I mean in the middle of the process, you will come across something like illegal expression.
But I think if you include some other part, I think for instance, people often do that, for instance, in the following thing, which, whatever, G or something, but in this way you can just put the G in general, like this, like the counter. People just hide it, like this. So they also do
If I take the Historian directly, and we just erase these two G and just use the Leibniz rule.
Like this. That's same as including this one. The same concept. That's why people omit it. Question?
Why the 4-point dimension equals 2? I'm not so familiar with this representation of spin. How does it connect with the spin?
So it's a good question. So with the model, this point corresponds some operator, and that is labeled as. So that's the primary field. So some primary operator. So this V is one-to-one representation of SU2 spin share representation. One-to-one representation. Yeah. So that's why it's with the model. So its action is written by G and C equals to 6, right? G2, right? And G is 3, right? Everything, all those primary operators are rated by representation. That's you can treat as a fact. Yeah. Thank you. Integer representation. J is the number of boxes. So number J is the number of boxes. Because in one part, so this is the lowest two dimensions. So this J is So as you know, the dimension is the spin representation. Representation of this 2J plus 1 dimension. And that is linear in J. Therefore, if you increase J is of course up to the half. Possibly. C1/2 is the lowest dimension. So therefore, I just always assign the number of elements in the J, number of J. It's just you can just consider the rule in J. Half corresponds to the left tableau with one row in J. That's the rule. This is actually nothing, zero. It's the same as zero. So you just assign the height is only like a 1. So this is equal to the previous information. It has to be 1. And since this violates the rule of the height of 1, so it is Okay, shall we start? Resume. So, do you have any other question about some previous lectures and so on? Before we resume, whatever question you have, you can ask me about lecture, exam, homework, how to grade, and so on. This is the last lecture you should ask. If you have a question. Does anyone have a question about the lecture, previous lecture, or homework, grading, final exam? No? Then I'll move on. If you have questions, just tell me. This is the last chance almost. Linear geometry, not about the bundle, or I mean, tangent bundle and so on. I mean, it's about how, I mean, curvature, crystal per symbol, so on. Given the metric, how to compute any curvature and so on. Just get used to it. I mean, you guys did lots of homework, so don't worry so much. Okay, so just get used to, just review how to calculate curvature and so on, or crystal per symbol. And given the metric, that's it. I mean, to be honest, I don't want to have this exam, but it's a magnitude by the determinant. Yeah. So I told you, the necessary formulas are all written in the exam, so don't need to memorize. That's why it's a beach one. I told you. I don't know, my tones are horrible. I don't know how my tones are horrible. Any other question? So then let's talk about a bit more complicated example of modular space. So modular space of triangle. So A is triangle. And then the equivalence relation is indeed a similarity. So you know similarity, right? So if you have the if angle are all same, it becomes similar. It's called similar. It's very similar. So if angle all are all same, it's called similar. So you can just also rotate inside wherever it is. Okay. So therefore, and I call modular space of triangle is indeed all the space of triangle divided by equivalence relation, up to similarity. So this is indeed, you can fix the length of, let's go A, B, C length. So if you fix the total parameter, it's total parameter A plus B plus C is equal to 2, then you cannot scale, right? Already you cannot scale if you change, and also you have to impose the following condition, the triangle relation A plus B must be greater than C, and then A, B, and C. Okay, so you can easily see that if you fix a parameter and then just impose triangle relation about the length of edges, then you can classify all the triangle up to similarity. Okay, that's you learn from Euclidean geometry. Okay, so what's this space? It's very simple. Let's see which one I should erase. Maybe here. So I'm doing a very simple example. So you have A, B, C, and it's the first condition here will give you the following condition, the following plane indeed. The following plane, right? 2, 2, 2. Okay. The first condition will give you this plane. So you can easily see it's just in the one linear space, it give you the plane that actually intersects 2, 2, 2. And then, okay, let's do step by step. The third condition will give you the following place. Anyway, so A has to be, less than or equal to B. So A has to be less than or equal to B means that this has to be this place. Okay? What am I doing here? Am I correct? Right? So if you pick this point, A is greater than B. Okay, definitely. On this point. And similarly, so B has to be greater than, less than C means that so you just pick, this point. Okay? You have to pick this triangle. Okay? And then second condition, A plus B has to be greater than C. We impose the following condition. So A plus B, the A plus B, the constant A plus B is equal to constant is really this line. Okay? This line. So therefore, this means that if you just put the line here, I think it should be proportional here. The parallel to here. Okay? So the A plus B has to be greater than C means this triangle. Okay? So the modular space is in this red triangle indeed. And just make it bigger. I'm going to make it bigger. So this triangle makes it bigger, and indeed it sits 2/3, 2/3, 2/3, and 1/2, 1/2, 1, and 0, 1, 1. Yeah, so this point corresponds to this point, and this point corresponds to this point, and this point corresponds to this point. Okay? And of course, at each point you have a triangle. You have some triangle. Well, I don't know, that's some triangle. Okay? Some triangle. Some triangle. And then, of course, if you move to the boundary of modular space, for instance, something special happens. In fact, you cannot include this one. So, as I mentioned, A plus B is strictly greater than C. So therefore, this line shouldn't be included. Okay? Therefore, this one. The reason why is that if you move to the boundary of, if you around this point. Okay, around this point, the triangle look like this way. Become very, very narrow. Okay? And if you hit this point, I think I should write it like this maybe. I don't know how it look like, to be honest. I have to do careful calculation, which point corresponds to which length. If you hit this point, it becomes line. So it becomes really thin line, and if you move to this point becomes hits to the line, the bottom. Therefore, no longer it's triangle. Okay? So therefore, you have to remove the bottom line. Okay? At the bottom line, the triangle degenerates to the line. So this point at the boundary here, the bottom. Degenerates to line. Okay. It's very similar to what we have solved in the examples here. So if you go to the boundary of the modular space, it becomes degenerates to the point. The similar phenomenon happens. Once you move to the boundary of the modular space, it degenerates to the line. So what happened is this line corresponds to this one. Okay? So this line, B and C are the same length. So therefore, it's called isoscele. BCA, and this length is the same as this length. So this is called isoscele. I don't know how to spell it. Isoscele triangle. Okay. So how do you call it in Chinese? Like this way? I mean, in Japanese, this one. How do you pronounce? Write it in Chinese? Huh? Can you write them? You can write them. Okay. Thank you very much. Oh, but you write it in the old character, more simplified character, on purpose? It is simplified already. Okay, good. Okay, I see. It's a bit different from Japanese. Oh, but I can understand. Yeah, though you can understand also. Anyway, then let's erase Japanese version. Anyway, that's called isoscele. And this part, now A and B are the same. So this part becomes like this way. A and B are the same. So therefore, this angle becomes more than 90 degrees. Whereas this is less than 90 degrees. At this boundary. And of course, there is some special point here. This is equilateral. So this is equilateral triangle. So is it? Oh, how do okay. So in Japanese, this one is Jen. Is it same? Oh, good. Okay. So even though my tones are horrible, you understand it. Okay. Okay. So it's the same. Good. So this capture very like a particular. So at the boundary, at some boundary, the triangle degenerates to the line. Okay. But on the other hand, if you go to the other boundary, something special occurs. So isoscele triangle has a Z2 symmetry. So you just do that rotation along the line in the middle. Okay, you have a Z2 symmetry. Okay, you just. But triangle. Equilateral triangle has the dihedral group. It's called dihedral group, which is generated by R and S, such that R cubed is equal to S square is equal to SR square is equal to 1. So R is just rotation by 120 degrees. Okay, R generated the rotation 120 degrees, so that the R cubed is equal to 1. S is just, again reflection. Reflection along this angle. So this is the it's called dihedral group of the ABC. So dihedral group. Dihedral. Okay. So at this point, so again something very special thing happened. So this is modular space or triangle. So that at each point you have some triangle of a modular space. Okay. Hopefully I can get to the end. So I took almost all the time of this week I prepared this lecture myself. Okay, now, so we classify, so we just consider here, now change the game. Change the game. So oriented. You just consider orient triangle up to similarity. So we call it tilt. So oriented means that you just consider ABC, and then you cannot change the cyclicity of ABC. Okay. So for instance, let's see. Write down. Let's consider the following. This is the same as. How should I? Oh yeah. I think I should write it like this way. So they are similar. So let's consider the following triangle. Right angle. So then let's call this one is alpha and beta, and alpha and beta. Okay. So there, in previous example, at the previous, if it is no orientation is imposed, they are similar. But now we cannot change the ordering of ABC. Okay? So then they are different objects. Okay? Different objects. So they are not similar. They are not equivalent. Not equivalent. So you just encode the ordering of ABC so that they are not equivalent, even though they share the same angle. Okay. Then what we need to do is indeed you just consider that do not impose this condition, but you just impose the condition like this way. Sorry, the other one. So it's the condition is just only this. So so since I just incorporate this right angle. So this is in English it's called right triangle. Okay. In Japanese, is it correct? In Japanese, this one. It's same? It's different? Same? So without this one or something? It's same, exactly the same. Okay. Probably you guys import from Japan. Japanese. Okay. So this is the right triangle. So I don't need to erase. Right triangle just sits around here. Sits around here. This is a square plus b square is equal to c. Let's have you will see. So if you change the game for oriented triangle, then that's impose this condition. You just the same as doubling. Doubling modular space. What was the word comment? Yeah. You're just doubling the game. So, yeah. Oh, sorry. I think it's a bit. Okay, my hand drawing is horrible, so that's why it doesn't move like this. So in other words, so the modular space is double. This way. However, at the boundary, you have to be a bit careful around the boundary. So around here, the triangle. Sorry, so triangle look like this way. So B, A, C. Okay. And indeed, so let's A, B, C. So here, I just got confused. Is it correct way to parameterize it? I just got confused. Sorry. I'm just wondering if this is correct way to sorry, so this is the same. Here you have the B is equal to C, right? And you have a, no. A is equal to B. Good. Okay, so then it should be okay, but they should be identified. This place has to be identified this way. So at the end of the day, so what you have is something like a this kind of object. So you just identify opposite edges by identifying. But I don't know why it's still as an oriented triangle are they same? I just got confused. Okay. I'll explain why it has to be the case. And then this. So how do you pronounce it? 犄角 三角形. Okay, 犄角三角形 is located here. Okay, so that's the case, and then yeah, I don't know why the oriented stuff is like this. To be honest, it doesn't look like that. Yeah, I don't know why. Let's call alpha, beta, and gamma, right? Alpha, beta, and gamma. Am I missing something? Oh, I see what you mean. Okay, I see. So here, to move one to the other, you have to do the reflection and then rotate. I think that's what you need to do. On the other hand, if you do the rotation, it's okay. I think that's what you mean. Yeah, fine. That's so you can do the rotation. But here from move one to the other, so you have to do the reflection and the rotation. So if you don't include the rotation, you can move one to the other. Okay, so this is the modular space of oriented triangle up to similarity. There's another way to look at this problem. You can always consider the following. So you just consider the upper half line. The upper half line. So you just put the triangle, and then you always put the one edge to the B1, scale to the one edge to the B1, and put the C minus F. Oh my goodness, the other one. C and B. And put this position is complex number Z. Okay? It's located Z. Okay? If you change Z along the upper half plane, you will change the angle. You will change the shape of the triangle. Okay, so you can just move around the upper half. Okay? Then, if you do that, indeed, so that we put Z is equal to A minus B, and then C minus B. And if you do the following thing, so B minus C divided by A minus C, and you get 1 minus C. So now, so we have A minus C is, A minus C is what? A minus C is Z minus 1, right? Clearly Z minus 1. And B minus C is minus 1. So minus 1 divided by Z minus 1 is this one. And also, you can have the similar thing. C minus A divided by B minus A. This is in the same trick, the same trick with this. They are all similar triangles. And as you already know, this upper half plane is the action by PSI to Z. That we already did many times. This transformation in homework. Okay, you already see the action of upper half plane of PSI to Z. So this guy is indeed associated to 1 minus 1, 1, 0 in PSI to Z. And this can be understood as the 0, 1, 1 minus 1, maybe? No, sorry. In PSI to Z. Okay? Just plug this matrix into here, you get this transformation. Okay? So therefore, if you call this guy, it's omega 0, omega 3, and this is indeed omega 3 squared. That you can easily see. So if you do the metric multiplication, the same thing, you get this one. And then, of course, omega 3 cube is what? Omega 3 cube is what? This times this is what? Huh? Good. This is identity. So therefore, the group generated by omega 3 is indeed Z3 inside of PSL to Z. Okay? So it's generated by 1 omega 3 and omega 3 squared. Okay? It's a cyclic group. Okay? Do you understand? Omega 3 square. And if you multiply omega 3 again, you get something 1. It's secretly inside of PSA2. So therefore, modular space is there similar triangle. The position there is similar triangle. So therefore, modular space indeed upper half plane I don't think I can get to that, unfortunately. But it's better not to rush. Triangle and tilde is indeed upper half plane divided by Z3. Okay, let's look at how. Let's try to look at how it looks. So then, this is indeed something like a. Okay, I think it's okay. Zero, 1. Okay. You just consider the following two hollow cycle, and the modular space is indeed here. And then, of course, this is rho, which is e to the 2 pi I divided by 6. Okay? And this arc is identified as arc. Okay? And it's very similar to what we have seen here. So you just, this is, modular spaces look like a triangle, but now this edge becomes arc here, and this edge become arc here. Okay? And why Z3? So indeed, as you can easily see, if Z is equal to 1, okay, if Z is equal to 1, which means this point, okay, this point, the transformation here will move to infinity, okay? You can see infinity. So therefore, indeed, and also if you put the Z equal to 1 here, it becomes 0, okay? And therefore, what's going to happen is as follows. This region is mapped to this region by 1/1 minus C. Okay? And the further Z minus 1 over Z will map this white part to this part. Okay? And they form Z3 subgroup, Z3 secret subgroup. Okay? So H upper half plane of Z3 is really quotient by white, purple, red circle. So this is 1 omega 3 square and 1, and this secret. Okay, and of course there is something invariant. So this point is invariant under this Z3 subgroup, as you can easily see. But that's what happened in this equilateral Zheng situation. Okay, Zheng situation. And then here, at the boundary you have this one. How do you pronounce this one? Then yeah. Okay. Okay, Dihedral. Okay, so Dihedral it sits on this boundary. Okay. Okay, and of course, right triangle is sits in this circle. Okay, right triangle is this the half circle. Okay, So that you have a right triangle, right? Always, it's right triangle. So this is very similar to what. So they're just rescaling this the modular space by different language. You get this one. Okay. And then there's a nice way to identify. So as I mentioned, this part should be identified this part. Okay. So a nice way to identify this one is first bring this white part to the this white part is bringing to here by this transformation. What was that? Okay, so you have the edge, the 0, 1 row, right? 0, 1 row is mapped to, sorry, okay. Row 0, 1 is mapped to 0, 1 row square. This is row square. So if you plug in row into here, so the numerator is 0. So row is mapped to origin, okay? And then if you plug in 0 here, Z0, you get the 1. So 0 is mapped to here 1. Okay? And indeed, and the 1 is mapped to row, if you do the row square, if you do the calculation. So more like you just, let's say, so rotate and bring this arc to here, and this arc to here. Okay? So this purple part is become purple edge become here, brings to here. Okay, and to identify purple edge, you just use Z goes to ZQ, and then bring it to just how to say 3 times the angle. Okay, then it becomes the modular space is indeed unit circle, unit disk. And the right triangle part, this right triangle part is definitely this way. Okay. And this part it will be mapped to. So this purple will become here, and the red becomes like this way. Okay. So this is a modular space, okay, of triangle. So at this purple point, you have this. It's hard to. Okay. Isoscele triangle. It's better not to humiliate myself by using horrible my Chinese. At this point, you have a degree, and then at in here, you have an equilateral. And this red part is indeed a right triangle. Okay. Right triangle. And then at the generic point of the modular space, you have some generic triangle. Maybe let's make it more generic. Like a generic triangle. So that's the modular space for triangle. Okay. Let's talk about the modular space for Riemann surface. So let's move on to modular space of Riemann surface. So, unfortunately, I don't have so much time to work on it. So A, so modular space or Riemann surface. So A is indeed a Riemann surface as a complex manifold, one-dimensional manifold. So if you have a Riemann surface, you have point and you have an open patch, you just map this one by into C. Open patch here, and you have another open patch here. You have another map to C to here, and between them is actually given by holomorphic map. So it used to be just differentiable map, differentiable invariable map, but now we impose holomorphicity as a complex manifold. The equivalence generation is so-called biholomorphic. So in other words, if you have a two Riemann surface, you have a map F, but this F has to be holomorphic and invariable. Both F and F inverse is invariable, holomorphic. Okay? So holomorphic means that, of course, you have again, it's a similar thing as what we have learned. So this one is coming here, and this one is the map to open patch inside of C. And this map is indeed, so this compose inverse F, and this map is holomorphic. Okay? So that's what we mean. And biholomorphic means you have an invariable map. And then of genus C. And then Mg, indeed, A is equivalence generation. Now, unfortunately, I don't have time, so I will talk about only genus one case. Lecture note, I just spent more bit about sphere with puncture, but I'm going to skip due to the time constraint. So we know torus genus equal to 1 is a torus. And this can be constructed by plane, complex plane divided by lattice. Okay? So given the complex plane, you have a lattice. Anyway, lattice. Oops, sorry. Has to be parallel. Okay. And then this lattice lambda is spanned by omega 1, omega 2, which is a vector of, let's call B1. And B1 and B2, which is this one. So then you can just, if you quotient, you just identify top and bottom, and then left and right, you get the torus. Okay? And if you change, so as we saw in the case of the triangle, if you change the point in modular space, you would change the shape of the triangle. Okay? As you move around the modular space, the shape of the triangle will change. Okay, the same thing happens in the torus case. As you change the lattice, the shape of torus will change. Okay? For instance, if you have another lattice, you can have such a lattice. Okay? Now you have identified this top and bottom and the left and right like this way. Clearly, this parallelogram is different from this parallelogram. How do you call it parallelogram in Chinese? Is it same? Oh, it's the same. Okay, good. We can communicate by writing. Okay. So 平行是变形. Okay, good. Okay, so then, so as you change the lattice, you can change the shape of the torus. But there is some effect you can consider. You have to consider, so unfortunately, I don't have 10 minutes left, so let me be schematic. So when you set B1 do the transformation, so you can do the transformation such a way that the ABCD again sits in PSR to Z. Z means ABCD has to be integer, and then determine equal to 1. So then, so for instance, B prime and A prime can be like this way. B1 prime, B2 prime. The lattice defined by B1 prime, B2 prime are the same as the before, B1 and B2. Okay? So therefore, if you use the PSZ transformation, the lattice structure doesn't change. Therefore, lattice is received as an automorphism of PSZ to Z. PSZ to Z. Now, precisely, if you consider only the shape of the torus, you can do the similar thing. So you set tau is equal to omega 2 divided by omega 1, and then omega 1 is scaled to be 1. Therefore, what's going to happen is as follows. So you have upper half plane again, and 0 and 1, and you just specify the point tau. That will give you lattice structure. And tau prime, which is defined by tau prime is again omega 2 prime. So not omega. Sorry. So this is B2. Sorry, B2. And I said B1 goes to 1. The similar thing. So this is B2 prime, B1 prime. And this transformation is indeed the same as this one. So by this transformation, it doesn't change the shape of the torus. So now we just consider the upper half plane. Okay? And if you change tau, you have another torus. So if you change tau, you have another torus, okay, with different shape. But you have to identify tau prime and tau up to PSL to Z. So what's happening is PSL to Z. The modular space or Riemann surface of genus 1 is upper half plane divided by PSL to Z. And I just give you an answer how it looks like. So this PSL to Z is generated by two elements. One is T called T transformation 1101, S transformation which is 01 minus 10. In particular, so T transformation will map this one to here. Okay. In other words, this T move to tau goes to tau plus 1. Another one, S will give you tau goes to minus 1 over tau. If you plug that one into here. In other words, so you swap one and tau essentially. Swap. So then what's going to happen is as follows. So this part is indeed a modular space or Riemann circle with genus 1. So this part is called fundamental region, and it is identity 1, but tau T transformation moved to shift by 1. So this 1, 0, minus 1, minus 2, 2, 3, minus 3. And then the S transformation bring this part into here. So this is S. And this is T inverse, and so on. So you can just bring many places into, for instance, this is T times S. By S transformation, this region is mapped into here, okay, in S. By T transformation, this region is mapped to here, okay, and T inverse is mapped to here. By using SA2Z, this region is mapped to anywhere in the upper half plane. By using this S and T matrix, so you can just fill out the whole entire upper half plane by using S and T. Therefore, quotient space is here. So this is called fundamental region or fundamental domain. And then, of course, you have to identify this part and this part. Okay? You have to identify the edges here, and also you have to identify this purple part and this white part. Up. So this red part is moved to this red part by T transformation. By S transformation, this purple part is identified this white part, white arm. Okay. So at the end of the day, so it looks like as follows. Unfortunately, I don't have a time to talk about any. Okay, so that's what's going to happen. So this point I is really this right angle lattice. Lattice becomes right angle. And this point, the lattice becomes really two copy of Shen San Shin. Anyway, so all the lengths has to be equal. Okay? And this is 120 degrees. Okay? At this point. Okay? If you go to infinity, the torus look like this way. Torus look like the one is okay. So the tau goes to upper infinity. So it's an infinite long the torus. Okay? And then by up to S transformation, it goes to 0. This up to I infinity goes to S transformation goes to 0. Which means the torus it becomes really, really small. And at the degenerate, and it degenerates. So in other words, torus goes to very small, spin really flux like a flux tube. Becomes 2. At the end of the day, it becomes circle. Okay? At the circle. At the I tau. So the torus degenerates to the circle. So this is the modular space Riemann surface. And what the 1857 Riemann has written mg has to be 3g minus 3. Complex dimension. So which means real dimension is indeed 6g minus 6. And this is true indeed, of course. And then to construct this one, you have to watch my lecture and simply make this. Let's stop here. Unfortunately, thanks for bringing this one, but I don't have time to use. I plan to show some mathematical file to. I don't think I have time. I think within a 1 minute bell will ring. So, but thanks for bringing up. But I will return it. Sorry. Okay. I mean, if somebody wants to listen more, I can explain a bit more. But people must be hungry. Yeah. Let's stop here. And if you want to listen a bit more continuation, I can stay here. I can explain. Just tell me. Let's stop here first.